First of all, welcome everyone. My name is Martin Brown. I'm with Edis Research. I joined Edis Research in early 2014. Before that, I was actually based in Germany, KIT, where I got my degree, and using USERVs and computer radio for a long time. You know, as a customer first. Now I'm actually working on their development, and in particular developing RFNoC for the last couple of years. And I have the pleasure and honor of working with Jonathan.
Hello everybody, my name is Jonathan Pendulum. I've been at Edis for just over a year now. Before then, I went and got my graduate degree at Northeastern University in Boston, master's in computer engineering. There I studied and researched heterogeneous processing, especially applying it to software-defined radio. Before that, I'd worked in the defense industry for about 5 years, and my bachelor's degree I got from Purdue University in electrical engineering. And as well, one of my main focuses at Edis is working on RFNoC. I am the FPGA lead, and it's great because it was a continuation of my graduate work of doing heterogeneous processing.
Okay, thank you very much. So, a couple of administrative things. First of all, we do not have handouts yet, but we will make these slides available to you somehow. So maybe through the wireless symposium website, but worst case, you can always contact us. Also, I've prepared a little handout, one page, which you could pick up at the back, where the water bottles are. You can also find my business card there if you need to contact me or Jonathan. Oh yeah, and this talk is split into 2 halves, as indicated on the agenda. So before the coffee break, we will be talking about RFNoC in general. So this will be the overview. So if you don't know anything about RFNoC, I strongly recommend you hang around and follow that part of the presentation. Then after the break, we will go into how to actually develop it. That part will be very technical, very detailed, very hands-on. So if you actually want to use RFNoC and start getting your hands dirty with it, you should definitely visit the second part. And if you already know what RFNoC is, you could actually skip the first part and come back in at the second part. We've kind of laid it out that way. But if you don't know anything, I do recommend hanging around for the first half. Finally, we do encourage questions. So we've done this presentation on RFNoC in general several times now. We have not done the tutorial part. So, you know, that's something that we'll be iterating on. We'll definitely improve. So, any questions, just put them right out there. Immediately answer them. There'll be no unclear things that we put on our slides. If you do have questions after the presentation, obviously you can always approach us while we're at the conference. But I mean, like say next week or in the future, if you want to ask us things, the place to go is the users mailing list, which is made popular through our website and the radio website. Also, the radio mailing list is highly recommended for general discussion in the area of software-defined radio, etc. Okay. Okay, but that's all the boring part. Let's talk about RFNoC. Okay, this is the first part of our presentation. We actually have several slide decks that we'll be rotating through. But this is sort of what we talk about when we talk about RFNoC on a high level. So what does that actually mean when we're doing host-based software-defined radio? Then quickly lay out the actual architecture, and then we'll be showing RFNoC. So fingers crossed, you know how live demos work at live presentations, but we've been very confident, very lucky with that demo so far. Okay, so software-defined radio. At this conference, I'm not going to explain what that actually means, but I would like to repeat that when we talk about software-defined radio, these days, usually what we actually mean is a setup like this, where we have a host-based driven design. So we have a separate box. In this case, it's a USART X310. We actually have one of these here. So if you want to have a look at that, I'm going to attach it if you haven't seen it before. You can come up after the presentation, and we'll actually use it for a demo. Yes, so we have a separate SDR hardware which we connect to our PC. And even for our embedded system, the setup is basically the same. all of these two devices become physically melded and like very close together. But what we always have is this like separation where we run this like general purpose code, and then we have RF hardware that we can control from this actual software. Now, if we look at SDR frameworks such as Radio, they've been developed for a long time. And so good software development practices are all applied. For example, like nice composability, modularity. We will all find these in typical SDR frameworks. So we can reconfigure them very quickly and actually show some examples of that. You know, we can like combine equalizers and filters and FFTs very, very easily. And we have all of these elements available, and that way we can very, very quickly build our applications. Now, if we go to the peripherals, and I've shown actually 2 examples of peripherals here, that usually ceases to happen. So, for example, you can see on the left side is Phosphor, is a very popular spectrum visualization tool. It runs on your GPU, but it is this monolithic application. You pass it IQ data, and it does everything with it. And internally, obviously, it calculates FFTs and windows and averages, but you don't really know what's going on. I mean, you can look at the source code, obviously, but you can't tap the intermediate stages. On the hardware side, exactly the same problem. And here it's even worse because we have these FPGAs that we can leverage, but we don't use the FPGAs in the same modular fashion as we do the software-defined radio frameworks. So GNU Radio is probably something everyone's heard. At the very least, you've read the name on your lanyard. It is in the free software world, it is definitely the most popular DSP or streaming framework that's out there. And it definitely can compete with most of the commercial frameworks out there as well. So very briefly, what does it look like? So first of all, we use C++, or we use a SIMD acceleration library called Bolt to actually write the signal processing components. As I mentioned before, these are nicely separated modules that we can then later combine. Python is also in there for easy setup, so we don't always have to compile or write C++, which can be pretty verbose. There's a lot of elements in there to graphically access data streams, or just simply graphically program. As you can see in the background, like all these arrows and boxes. Arrows and boxes are very, very common in all SDR frameworks, and GNU Radio has them as well. So this is the GNU Radio companion. You can see graphical widgets for spectrum analysis or scoping or whatever. And it has a very vibrant and active community, which provide additional modules that you can pull in. So GNU Radio itself will provide all kinds of basic DSP components, but then through our website called Cgram, you will be able to download modules for Wi-Fi, radar, crypto, all these things. You can just like latch them onto your installation. So RFNoC by itself is actually not necessarily tied to GNU Radio, so they are separate things. But we needed a SDR framework to actually get started and to showcase all of this. And GNU Radio is very popular in as research in our house, so that's why we're going to be using GNU Radio for this tutorial. Okay, so back to our initial problem. This is a very simple GNU Radio flow graph, and you can see it separates tasks into different blocks. And so this would be a OFDM transmitter, like packet-based or bursty modem. And if you actually look at these blocks and try to figure out where they're running, you'll see that all the interesting parts are on the left side, and these are all like nicely separated. And as a matter of fact, I don't know if I can't use my mouse cursor, but this OFDM transmitter, you can actually like zoom in another level, and you'll see keys and cyclic prefix, and etc., etc. And all of these blocks run on the hoods. On the right-hand side, we have the user control. Now, this also has different stages in there. It has like sampling rate conversions and according and all of these things, but there is no way for you to zoom in there, like see like the individual components, which is a shame because this means that we're using this entire FPGA-based device which is, in a sense, just as capable or even more capable than our GPP as an ASIC, like as if it was like this given device and there's nothing that we can do about it. And that is something that we want to break up, and that is why we developed RFNoC. Now, it would be unfair to call this block on the right-hand side a black box, because we can actually look inside all the source code, the FPGA source code is available, as are the schematics for example, this user of X310. So you can download all of these, but you won't be able to, as easily as in radio, like separate the components. Now, one thing that's interesting, and I've kind of alluded to this before, is that under this heatsink, you'll find a big and expensive FPGA. And as I said, like all the codes are available. You can even build the image yourself, and you'll see like FPGA utilization is at 30% or something like that. So like you buy this device and you get 70% unutilized FPGA space, and like very obviously the question arises, so why aren't you using that? Now, there is a very simple answer to that question. That is, developing on FPGAs is hard if you're used to the software workflow for several reasons. First of all, it's very different. Also, the development iteration cycles are much slower. So if you're using our most up-to-date branch of FPGA codes and you use Xilinx's Vivado to build it, you're still looking at like an hour or something between builds. So most FPGA developers, they actually have something else that they're working on at the same time, so they don't have downtime while they're waiting for compiles. And but even disregarding that fact, you might just simply not know how to develop FPGAs. And it's definitely not fair to put all of that burden onto the developers, because if you look at who actually uses this, there's a lot of, for example, research people, like at university. They know a lot about DSP and things, but even if you know about digital design, using Xilinx tool chains is a completely different skill set. And simply saying, well, how about you learn that skill set, I think is a bit unfair. And also, it's not like these people aren't doing anything, they're like developing codes or whatever, and I'd rather they like keep doing that. So as someone who builds and tries to sell USUBs, I think it's our responsibility to make that as simple as possible. So the people who are developing whatever kind of concept, they can actually stick to that kind of research, and they don't have to focus as much on RFNoC. On the FPGA development. That's why we have RFNoC. So fundamentally, it is imperative to understand that FPGA development needs to be made simpler, because it is simply not fair to the researchers to tell them to just learn the FPGA stuff. And that's and this is an example that will showcase this very nicely. So say you've just been to like your first DSP class, or one of your first DSP classes, and the first thing here is just like maybe it might be spectrum analysis, and you find Welch's algorithm described in your textbook, and you think, okay, well that's pretty simple. I can click this together in your radio, and you just like drop in all the components. So you start with your USUB source, and then you like apply FT and max square, window and averaging, etc., etc. And then you'll find this actually doesn't work for several reasons. And if you now in theory this is fine, but in practice it isn't. So if we have a look at this flow graph, then we'll find that, for example, maybe the FFT is eating up a lot of the CPU time. And you'll find that all of these operations are the kind of operations that are very, very easily implemented on FPGA. So this is exactly what they're really good at. There's lots of basic math, highly parallelizable. So there's really no reason to run these on your own computer. Also, as I mentioned beforehand, we have like 70% empty FPGA space. So that is already like a big question mark. Why are we shifting this over here? And the main reason why this would work actually is because I set the bandwidth in this example to 200 megahertz. 200 megahertz means 800 megabytes of data that you have to like pump into your application in real time. And if you're using a 1 gigabit Ethernet link, that's not possible. Like, it just doesn't add up. So the fact that this left-hand arrow is abstracting like a 1 gigabit Ethernet cable, which is obvious in this flow graph, like breaks this entire setup. But if you can simply move those right-hand operations on the left-hand side of the Ethernet cable, we would be fine because, as you can see, there's actually like a decimation component in this flow graph. And that was the idea of RFNoC. So Jonathan will talk a bit about the details of the implementation.
So one thing that we're really looking to do with an architecture for SDR would be heterogeneous processing, especially the GPP FPGA approach. As Martin had said, that there's a lot of these algorithms that make sense to run on the FPGA because they're highly parallel. And even if they're not so much as parallel, they can run just very efficiently in the FPGA versus you can be spending a lot of cycles on them in the CPU. And as well, you can do things like reduce the amount of data that's going over your transport, like the gigabit Ethernet, very easily in the FPGA. And so you can tap these higher sample rates while still having easy-to-use interfaces. And if we're going to come up with this architecture, we want to make sure that it's still composable and modular, like you see in your radio. You still want to be able to take those blocks and rearrange them any way you want without having to go into the nitty-gritty details of the design and rewire things up or just change entire parts of your overall architecture to support that. You want to make sure it's still easy to use, nobody's going to use it as hard. And you want to make sure that it has tight integration with these existing SDR frameworks. And to really visualize what we're thinking here is on this flow graph here, we do a lot of FPGA processing in the USERP, and then we do all this general processing in the CPU. What would be nice is if we had the ability to move that line where we want in the flow graph. Just wherever we want back and forth, so we can do processing in which domain it makes sense. And our solution to this overall problem is RFNoC, or RF Network on a Chip. And this is a new architecture that we have at Edis with the tagline that I like to say is we're making FPGA acceleration easier. We're doing heterogeneous processing. And what RFNoC really is at its core is a software API and FPGA infrastructure to take care of one of the hardest things in heterogeneous processing. And that is actually moving the data between one domain to the other. Specifically in our case, we're targeting GPP to FPGA. It's handling all that communication infrastructure. That tends to be actually quite difficult in practice. And also, what it's doing is it's providing the user these very simple to use interfaces, simple API, both in software and simple HDL interfaces in hardware, in the FPGA. Another really important thing is, these days you hear about 5G MIMO and these systems that it's becoming very clear that they're going to need some sort of massive distributed processing. And that capability is also built into the core of RFNoC to be able to do massive distributed processing. And as well, it's fully supported in Community Radio. We'll show a demo doing everything in Community Radio. So let's go ahead and take like a bird's eye view of the overall architecture. So you can see up here that on the top we have the host PC domain, we have a user application, Community Radio. Right below that is the UHD or the USERP hardware driver. That's traditionally how you talk to the USERP. That's your software API. In the FPGA side, we have a couple of interesting blocks here from the bottom. You have the radio core, some computation engines, a crossbar, and this ingress-egress interface. And I'm going to step through each block here and explain what they mean in detail. So first of all, on the user application and Community Radios, we have a very simple one, plotting frequency spectrum. A lot of people, when they first get a USERP in their hands, what do they do? Fire up Community Radio and just take a look at what they can see out there. But if you've already done that before, you may notice something interesting about this flow graph. Or if you think back of what was in Martin's slides before. That first block that was providing, say, sample data was called the USERP source block. But in this case, I have this RFNoC radio block. And so they look kind of different. Well, the idea with the USERP source block is it was this monolithic block. You have a USERP device. This is the block that describes it. All the FPGA and everything, details are kind of built into this block. It sets up all the DSP for you. There's no real, it's very coarse-grained. It's just, this is your USERP device. In RFNoC, it's different. Now we have this radio core in the FPGA. And that block that's in your flow graph is sort of a one-to-one correspondence, where that radio block in your radio, when you're setting the DSP settings such as the gain or setting what destination rate you want, those correspond to settings in the radio core block in the FPGA. What's also nice about this too is it means that for those of you that have used GNU Radio or have existing flow graphs and you're saying, wow, I want to use RFNoC, but I don't want to immediately change everything and do FPGA processing. I just want to at least do a first step. All you have to do is replace your usurp source block with this RFNoC radio block. And there you go, you're ready to go. There's no big hassle in moving over to RFNoC. And so as I said before, the hard part about heterogeneous processing is the communication infrastructure. So in this very simple case, what would happen is the radio core would receive RX sample data from the front end. It would packetize it, send it across RFNoC, so through the crossbar, through this ingress interface, up through the software layer, and into the GNU radio. Very simple in this case. But what's interesting is, okay, where does the FPGA acceleration come in? Where do I put my custom logic? Well, that's in these blocks called computation engines. That is the space provided in RFNoC for user custom acceleration. Now this right here, just by itself, is not really that different than what usurps have provided in the past. For instance, the N210 series did have some room in the FPGA, actual blocks set aside where you could go in there and add your custom logic. It wasn't the easiest, but if you had an FPGA experience, you could do it. One difference, though, between RFNoC and really it's a big difference, and in the way that things were done previously, is the fact that those blocks for custom acceleration and the N210 that were provided were in, you can think of it a chain, like a DSP chain. So it's after, say, the decimator, but it's before, or it's after like the DC offset correction. But they're in a chain. They're very linear. And RFNoC, these blocks like the radio core and the computation engines, they hook up to a crossbar. And that's where this NoC part of it, the network on chip, comes into play. Now we have a network where the radio core, computation engines, they're nodes in the network. And so therefore they can talk to each other in an arbitrary way. The radio core could send data to the host, or it could send it to a computation engine first. Maybe that computation engine would do something interesting with it and decide, okay, I'm going to send my process data back to the radio core. Maybe I'll send it up to the host. So you have this sort of arbitrary topology now that you can implement. And from our example flow graph, one block that obviously makes sense that you can run in the FPGA and it'll work really well is the FFT. So we can move that and implement it as a computation engine. Now one thing about RFNoC is this is one of the example blocks we already have. So in GNU Radio, what you would do is instead of coding one up, you would just take the existing RFNoC FFT block and drop it down. And what would happen is the flow through RFNoC would change. You would go, instead of the radio core to the host, now it's going to the radio core to the FFT block and then to the host. And that's where that network concept comes, is that now you can add blocks and the infrastructure itself will change to allow you to communicate between those blocks. And everything is also handled behind the scenes where you're not going into the FPGA and wiring up these additional or having to go into software and actually programming the crossbar yourself to do these connections. Instead, it's all handled for you. And that's one of the great things about RFNoC. Personally, I've been doing FPGA and SDR work for quite a while. And a lot of the traditional approaches is you just have a linear processing chain. And if you want to add a block in the middle, it can be really painful. Here, adding the block is quite easy. So now let's dig down just a little bit deeper and look at how does the communication occur between the radio core and the FFT. What does that look like? So one of the first things highlighted up here is we have our RX sample data coming into our radio core. It goes through the DSP part of the decimation, DC offset correction, various other interesting DSP functions. It then goes into these two blocks, this packetizer FIFO block. At that point, what's happening is the RX sample data is being packetized. Because not only is it a network, it's a packetized network. It's a packet switch network, which is very useful. So we send this packet up into the crossbar, and on that particular packet we have a header, and in there is a destination. The crossbar looks at the destination and says, aha, you want to go to the FFT block. So I'll go ahead and route your packet to the FFT block. When it gets there, it goes through a depacketizer, it strips off the header and everything, and sends it back into a FIFO. So from the user perspective, what you're having is a FIFO to FIFO communication interface, which is the easiest communication interface out there. You provide sample data until the FIFO is full, and you pull sample data out until it's empty. Nothing else you need to worry about how it's routing, what's the crossbar doing, I don't care. I'm just dealing with this FIFO interface. But what's nice about this packetization structure and the FIFO interface is that it allows us to implement flow control. One problem that you could have in the system is, okay, the FFT block, you know, I got, say, a 1,000,000 point FFT, something crazy. I load up all the sample data, and then I start crunching on it. And it takes me quite a while. But all the while, the radio core is still trying to stream data to me. Well, what can happen is as you're sending these packets, the FIFO and the FFT is probably not a point deep. That's not really reasonable. So it'll fill up. But if it keeps trying to send packets to me, well, then those packets could get lodged in the crossbar. And now all of a sudden you have a case where you have congestion, or even worse, if there's a lot of blocks flying to each other, you can even have a deadlock situation where just things can't flow through because there's this backup. Well, the flow control aspect comes in here because what happens is the producer, which is the radio core, actually knows how full or empty the consumer, which would be the FFT block's FIFO is. And it will not send data to it unless it knows it has space to receive it. And this is a credit-based flow control system. It's not totally new. If you look at TCP, it's a very similar concept of having windows and not sending too much data that you overflow that window. But what's nice, though, is the fact that we also have a deterministic place where data will be dropped. If for some reason the radio core is producing data too quickly, that data will be dropped at the producer, not in some block in the middle randomly somewhere, but deterministically it'll be right there at the producer. And that's nice because, say for some reason you are running your system faster, but you're okay with that because you can recover from those situations, you will know exactly where you need to sort of reset everything at and be starting at the radio core. And the great thing about this is all those blocks and all this infrastructure is provided by RFNoC. And as I said, the user has provided this FIFO to FIFO interface. Well, what does that actually look? I don't know if everybody in here has a lot of knowledge in FPGAs, but you have various buses that you typically use in FPGAs to hook things up. One very popular one is called Axis Stream. It's an industry standard. It was created by ARM, and it's extremely easy to use. That's what's great about it. It has some other properties that are fairly useful. For instance, data with Axis Stream has a handshake sort of setup that's very simple to understand, but what's great about it is data just kind of flows through your design versus other buses, you have to pay a lot of attention to how the data flows through. Axis Stream you don't. And what's also really important is that there's a very large library of existing IP that is Axis Stream compatible. And so, in the case of the FFT, Xilinx actually has an IP core. Xilinx is an FPGA manufacturer. They have an IP core that has Axis Stream compatibility. So when I was doing the FFT block, I didn't go and write my own. I just took the existing one and dropped it in, and it worked. And that was really neat how easy that was. Just drop it in, hook things up, write a little bit on the software side, and we're done. Which on the flip side, if you think about this from a very high level, what I'm doing is I'm talking from software into an FPGA, doing an FFT, and then getting that back. There's all these different interfaces I'm crossing, but I didn't care because RFNoC had it implemented and took care of it for me. Another thing that I'll bring up is in your computation engines, I'm only showing, say, one Axis Stream. I'm not showing any control status registers. All of that's built into RFNoC as well. I've just kept simplified diagrams, but you can have multiple Axis Streams in there. You can have control and status registers that you can access from software very easily. Another great thing, and this is a problem in FPGA design, is making timing. And a great thing about RFNoC is how we decide to handle this. Each one of these components operate in their own clock domain. Now that doesn't mean they have to be in a different clock domain. It just means that they have the capability to do so. So for instance, the radio core can run at, say, a slower clock rate, but the FFT core could maybe run faster, maybe because it's processing complexity on my algorithm I implemented. Not for every sample I send it can't output a sample immediately. It needs to do some number crunching. So maybe I run the FFT core at a faster clock rate, so I can match the radio core's output rate. And also, the nice thing about being in different clock domains is the fact that this improves timing. You're now taking your design and kind of partitioning it off into these little blocks. And when it comes to FPGA design, that does make timing one of these issues of how fast can I run my blocks a lot easier. It makes it easier to implement. Another thing I'd like to point out, RFNoC, the name RF Network on Chip, makes you think, okay, this is SDR focused or wireless comms. That's what you're going to use it for. That's not necessarily true. You can really kind of think outside the box of different sort of domains or different kinds of blocks that you could implement in RFNoC that could still be useful. The obvious ones, FFT, FIR filter, some sort of demodulator, modulator. Those are all, very clear applications. But you can also have things like cryptography that could be useful. Maybe some sort of compression, decompression algorithm. At one point, I was giving a presentation and somebody from the audience came up and asked me, they had a biomedical application. He said, oh, could I maybe use RFNoC with it? I said, sure, there's no reason. It's FPGA acceleration that's provided for you. There's no reason that it has to be sample data. It doesn't have to be INQ. It could be just some sort of integer or floating point data that you do some number crunching on. And another thing is the crossbar itself. I show that I have all these blocks hanging off there. You may think to yourself, well, how big can this crossbar get? As it gets bigger and bigger, the complexity becomes higher because I have all these this sort of arbitrary topology with all these different nodes trying to talk to each other. It becomes maybe resource intensive. And that's true. It turns out that the crossbar is the most efficient implementation would be 16 nodes on that crossbar. But the way that RFNoC is set up, there's no reason why you couldn't plop down another crossbar and hook them up together by using one port to forward to the other crossbar. And now you can just arbitrarily make it bigger and bigger in a sort of daisy chain, or you can even do some other sort of topology approach. But the next part is that means you can keep scaling. Not only within the device, but then, of course, the scalability part comes into play where if I can talk to another crossbar, I can talk to a host computer. There's no reason why I couldn't also talk to another device. And that's the great thing about it is that makes that massive distributed processing very easy to implement. Another great thing, and a traditional challenge in software-defined radio, is the fact that a lot of times our devices use some sort of transport that tends to have a lot of latency, like say gigabit Ethernet. You might have a millisecond of latency. And certain protocols out there, that's just not acceptable. 802.11, the MAC layer, and you can't deal with it. You need to be in the microseconds of latency. You need to do some processing, see if there's anybody out there using the channel. And after a millisecond, that's too long. By the time you decide, oh, I can use the channel, somebody else is already there. So with RFNoC, what you could do is you implement that sort of processing as a computation engine. And sometimes that can be difficult because if you're just writing regular HDL, it could be difficult to hand code. So instead, maybe what you do is you use a soft processor, which is essentially a processor that can run in the FPGA fabric. And in there, you could maybe code it up in C. And now you have still this low latency processing because it's occurring in the FPGA, but it's also easy to use. So we've really focused on, okay, what's going on in the FPGA, especially internal FPGA communication. How do we talk back to the host? Well, this next block up, I call it ingress interface, is a very generic concept. What the point of this interface is to basically do transparent protocol conversion. And what I mean by that is the host is the endpoint. So the distinction here is the ingress interface is not the endpoint, but the host. All that block is really doing for us is taking our packetized data that's in RFNoC and that's going across the crossbar, and maybe wraps it up in, say, a UDP packet, and then sends it up to the host. This allows us to communicate off the user, off our FPGA, to some other device. And some examples would be, we have PCI Express on our devices, 10 gigabit Ethernet. We have AXI, that's for the embedded devices, which is also different than AXI Stream, don't get me confused, but that's a little different. The other thing, too, is I said we have multiple crossbars, so maybe in that case, really it's not anything, it's just a wire going to the next crossbar. And as well, we have support for parallel interfaces. The X300 series has dual 10 gigabit Ethernet ports, and so we can support both of those. The next layer up would be on the host side, which would be the software API. UHD, the USERP hardware driver, does a lot of things. Mainly, though, it does configures the USERP hardware, setting up, say, clocks on the board, or gain, or tuning, things like that, an RF front end, or setting up some things maybe in FPGA that has to do with Ethernet. It also sets up the RFNoC FPGA infrastructure. We do it all from software, but the way that RFNoC is also set up, you could do it in the FPGA. There's no reason you could not. You couldn't have just a host, a system without a host. But in general, for ease of programming, we tend to have a host PC hooked up. Also, from the user perspective, it's providing you essentially read-write sample buffer data, or sample buffers, along with functions and interfaces to be able to read and write control and status registers. So we're back now at this point where I'm showing the radio port going to the FFT up in that block. Next, I would like to go ahead and show off the demo, which will see RFNoC in action.
So while Jonathan is firing up the demo, are there any questions until now?
So quick question. So in the new radio flow graph, initially you had this stream vector operation. Is there any of that like automated by RFNoC, or like is the user responsible for coding that up, or is that part of the denial of ID? Or
So in new radio, the block doesn't actually do it. That is a block that adapts stream signatures. It just makes sure that if you put in, so for example, the stream to vector, and you say that the vector size is 256, it just makes sure that every time you get 256 input samples, it gives you one output item. On the FPGA, we have a similar concept, called them stream signatures. And for example, the radio does not have does not know about vectors. Like it doesn't really make sense, like for the radio to think in vectors. So if you want to connect the radio to the FFT size, you need to make sure that the packet size that you output is something that the FFT block can handle. Now UHD will actually, and we're going to get into that later, UHD will actually take care of that. Will not necessarily do it for you, but if you set your flow graph in a way that would, like, the FPGA could handle, or might even crash it, it'll give you an error message, like a very descriptive one.
Is RFNoC part of UHD, or is that something you have to
Yes,
load?
it's part of UHD. It's very tightly integrated.
So what sorry, this is another part of the question, but so if you're a user and you want to build a FPGA block
Well, that's exactly what we're talking about today. That's the whole point of this tutorial. So the second half, I don't know if you were there at the beginning, the second half of the tutorial will be how to build your own RFNoC.
So as you start developing more and more complicated blocks that you want to put into the FPGA, like if you have more complicated demodulators and things like that, you know, if you talk to FPGA designers, they're going to say, well, I want to use chipscope, or I want to get into the FPGA and look at that. Are there any, have you thought about bringing out things to allow you to get any more insight into what's going on inside the FPGA?
Sure. I can answer that.
the question?
Yeah, sure. So the question is, what sort of debugging capabilities do you have in RFNoC? A lot of FPGA design engineers are used to using this program with Xilinx called chipscope. That is an amazing program. You know, when I started with FPGAs, I already had it. I think life would have been a lot harder if I didn't have it. Basically what happens is it is an integrated logic analyzer is what it really is, where you can look at various nets in the FPGA and see what data is flowing across them. That's really great. If you want to make it similar to software, it'd be like, okay, I can look via like a debugger, I can look at certain variables and see what values are there and how they change. It's very, very powerful, and you can use chipscope. I use it all the time with RFNoC. It's very useful. We also have a couple other tools. One that I'm going to talk about a little bit later is that crossbar. It actually keeps internal statistics of what blocks are talking to each other and how much. And that can be very useful where one problem with chipscope is you have to build a new FPGA design with those various probes in there to see the nets, and that will take an hour. If you have something to make it a little easier to help you kind of figure out what block might be causing your problem, say looking at the crossbar statistics, that can make your debugging iteration cycle a lot faster.
And one thing that's kind of, like, for us, it's already like so obvious that we sometimes didn't forget to mention it, but because of this modular nature, you're developing one block at a time, and you can just like drop it down in your flow graph, and you can like put in test signals and pull out the output of that test signal within your radio without having to set up anything special at all. So if you're just like testing a DSP, like, I don't know, does my filter actually produce the right spectrum at its output? You know, you already have all the tools to do that. You already provided it.
Yeah, exactly. And if you have like a backup in one of your blocks, you could also just disable blocks until you find the right one that's the one causing the backup.
Is there an easy way in your radio companion to determine the computational load of each block? In other words, figure out which block is your computational bottleneck and where you should look to start putting things on the FPGA?
I actually did that. So I did a Google Summer of Code project with Video Radio, and this had to do with using the Zynga ARM, dual-core ARM processor plus FPGA fabric in one device. And that was part of it. Was I was doing heterogeneous processing, so let's go ahead and offload something to the FPGA, and that's what I did is in GNU Radio, I used something called performance counters to see which blocks had the heaviest load. And I did the really simple one, like an FM receiver, and I found, okay, this particular filter here is causing a big issue. So I went ahead and replaced it with an FIR filter in the FPGA, and I got a tremendous speed up. So that's one approach right there in GNU Radio that you can get an idea of which block is the tall volt intent.
Performance counters?
Yeah. I said that right?
Yeah.
I want to make sure I did. Yeah, so that's a very powerful tool.
Okay, cool.
Yeah, so let's go ahead and go through the demo. So right here is the is an FFT flow graph. We were accelerating the FFT on the FPGA. One thing I'd like to point out is that, as Martin had said, you can kind of inject debug signals. That's what I'm doing right here is I'm actually injecting through here, these two, a sine tone and some noise. I'm adding them together and then sending that into the FPGA. So instead of taking data from the radio front end, I'm actually producing data in GNU Radio and sending it. And that's one of those really powerful debug tools where I could send in deterministic data. Or for instance, say I'm doing some sort of 802.11 system and I record that waveform, then I can just play that file back into my system and try to find out the problem deterministically. So that's what we're doing here. It goes into RFNoC. We go through our FFT core. Through here, you see this sort of grayed off box. It like splits. I'm going to show right here the fact that you can reconfigure the FFT core to change this output between, say, complex magnitude. There's also magnitude squared option, and so that's a great thing is that you can configure that. Then you go through a logarithm and the plotting curve. Make sure you turn on my X300. That helps. Give it a second to warm up here. No? And here's our FFT. I can change that frequency back and forth. One thing that's interesting about the Xilinx FFT core, it actually outputs the data in natural order, which is kind of a jumbled-looking order. To humanize, typically we like to have negative frequencies on the left, DC in the middle, positive frequencies on the right. So in the FFT block in the FPGA, I implement an FFT shift to do that for us. But the great part is the FPGA is very good at doing that sort of math. Or just really rearranging of data. You don't have to do it on the host. Nice thing to offload as well. Another thing is you can take the noise amplitude and let's reduce that. Let's keep reducing it lower and lower and lower. And all of a sudden you see these really weird looking dropouts. One thing is when you're in the GNU Radio environment, everything's floating point. So you have tremendous dynamic range. And you don't think about as much on the fixed point case of, well, what if I reduce my signal level lower and lower and lower until eventually the FFT starts outputting zeros in its bins because of just how low I've reduced my signal. So in the fixed point case, that could happen. You could have zeros coming out in the FFT bins. Well, what happens then when you do a logarithm of zero, of course, is you have negative infinity. And so in this case, it's being shown. You're having these dropouts. And that's one thing, there's a couple of things when you're doing fixed point in the FPGA that you have to pay attention to. There's just various rules and bit widths and how you need to do these things that it's worthwhile to pay attention to. So that is the FFT case. Now the next thing I'll show off here. Oh, sorry.
What's your default window?
So that one was rectangular. You asked me this last time at USDR, and I didn't say it. I should have. In this example, I have the rectangular window, and I also used the Blackman Harris window as well. So,
Good job.
yeah. I actually felt really bad afterwards. I thought, oh, I didn't actually say what window I ended up really using.
Well, your input signal must be bin centered, otherwise you wouldn't.
Yeah. So that last case, exactly. I didn't allude to that, but you see that really sharp spike. Well, I'm generating deterministic data, and if I align everything properly, I can have my signal right in the middle of the bin. And without a window, with just a rectangular window, you can still have an extremely sharp spike because the ends of the signals line up perfectly. With real data, you wouldn't see that. And I'll show this right here on this example. So this one is similar to the other one. The only difference is I added an FFT, a window. And what I'll do is I'll offset where my signal is at, and now you can see those side lobes come up there. Now they exist, and I have the noise up here too, so we'll pull that down as well. You can see it a little bit more clearly. Now I can go from, the nice thing about RFNoC 2 is you have the ability to change the design as it's running in terms of, say I want to change my window. I'll go from a rectangular set of coefficients, if I can click on here, to say, I didn't even write it first, to say a Black Harris window, and so you get, and what's happened here now is that the side lobes have been reduced a lot at the expense of the main lobe getting wider. And another thing is, here comes again that issue where we have fixed point math, so it looks like the signal's dropping out. What that really is again, the FFT is outputting zeros in those bins. And if you increase the noise, it's not because the system's glitchy, it's like I said, they're just zeros.
One trick, you add an epsilon before the log, and that keeps you from going.
So, yeah, I did do that. Yeah, I didn't end up doing that though in this case because it made the flow graph look a little different here. Okay, so just to make sure we don't go too far in time, I'll go through another one. It's the FIR filter. Let's see here. So very similar. We have a noise source. In this case, we have an FIR filter, and we're going to change the coefficients on that at runtime as well. So let's fire this one up. So we have our set of coefficients. We can go between, say, a narrow set and a, if I can click here, there we go, a wide set. And let me go ahead and, there we go, set the max hold. And we'll go back down to the narrow set. And so you can see that at runtime you can flip these coefficients, similar to the window case. And finally, one flow graph that I'd like to show, a newer one, is that Welsh's algorithm looking at the spectrum and trying to run things at, say, 200 megasamples per second in the FPGA while still being able to receive data over gigabit Ethernet. We actually have that working right now. We call it the vector IIR flow graph. The reason that it's vector IIR is because that moving average is actually a set of IIR filters that go across the FFT bins, and so that allows us to go ahead and throw away some data. That's this RFNoC keep one and n block, so we can decimate pretty heavily. In fact, I do 2K decimation, so I really reduce the sample rate. And in this case, I'm actually having it hooked up to the radio block, so we'll see what we can see out there. I don't know in this room if we'll have great reception or not. Okay, so we're looking at, I think, 920 megahertz, and we're seeing some interesting looking waveforms here. The nice thing about our system is that you can tune very quickly, so I can kind of sweep across the frequency spectrum, and I think there's that guy there. Maybe go down to FM and see if we can see. I think we can see a couple of FM stations if I get it right. Yeah, so I think we see a couple maybe FM stations. One thing is that the FFT here is only 256 points, so doesn't have a lot of resolution. But otherwise, that's the great thing about this is that we can run this at, say, 200 megasamples per second, and you can get this really wide spectrum and see it in real time, which traditionally with GNU Radio that was impossible. First of all, at 200 megasamples per second, really because of the computational overhead. I mean, if you had a really beefy system, maybe it could be possible, especially using dual 10 gigabit Ethernet on the X300. But in this case, I don't show it. Actually, I guess it could go fast. In this case, using HTOP, looking at my processes, my processors, I don't really have much going on. It's very, at the top here, you can see very, very low utilization. So those are the demos. Let me go back to my presentation. And so just to summarize really fast, we do have a second part coming up, but as a summary for the first part, we've created this simple architecture called RFNoC, RF Network on Chip, that allows us to do heterogeneous data flow processing, FPGA, GPP approach right now. It'd be the future, we extend that, maybe that include ideas like GPU and DSP, but right now it's FPGA CPP. We've implemented several interesting computation engines. We've integrated with a high-level SDR framework in the radio. It's portable between all of our third generation devices, so that would be X300, X310, and E310, and also going forward, this is the architecture that we're using. So future products, they're going to support RFNoC. And it's completely open source. All the source code is available on GitHub, not only in UHD, the software side, but also the FPGA side. And we are right now in our beta release. We're in beta because there are still some changes that we're doing here and there to improve it. But we have a Wikipedia, or we have on GitHub, we have a wiki, that's the getting started guide, but we'll also have a quick getting started guide in the back there that you can pick up that I highly suggest. Also, if you start using RFNoC, you have problems, 2 things to do. Go to the USERT mailing list and post questions, we'll answer them. Also, I believe it's rfnoc@edis.com. You can send us emails, and all the developers would get it, and we'll reply to them. So that is our first part. All right, so welcome back. This is the second half. We're going to do a deep dive into the FPGA. We're going to talk about a lot of the nitty-gritty details. Feel free to stop me at any time to ask questions and to clarify anything that maybe you don't understand. There is a lot on the FPGA side that I'm going to get to that is very interesting from the RFNoC perspective. But on the flip side, from the user perspective, when you're implementing it, you may not have to know it, but I think that you'll find it interesting to know exactly what's going on behind the scenes. So first of all, I'm just going to talk about getting started with RFNoC, especially on the FPGA side, what hardware you need, how to build things. We'll go into the anatomy of a computation engine, what's in there, what's RFNoC providing, what do you need to hook up to, how does it all work. We'll go through the FFT block walkthrough. And then finally, I'll give some design tips that, some basically things I've learned while developing computation engines that you might find interesting and help you from maybe running into issues that I ran into. So first of all, what kind of hardware and software do you need? Well, on the hardware side, of course, you need a computer or a laptop. That you can't get away from that. One thing you might need, though, is a decent amount of RAM, typically more than 4 gigabytes. That's because when you're making FPGA images, they tend to use a lot of RAM, especially on the larger FPGA side. You could maybe need 8 gigabytes of RAM, maybe even more. It's better now with the more modern tools, but you still do need a decent amount of RAM. And it's RFNoC supporting all the 3rd generation devices like the X300, X310, or E310, so you'll need one of those devices. As well, what you'll probably find useful on the E310 is having a Xilinx JTAG debugger module, so you can run chipscope. On the X series, though, it turns out that you don't need that because we have a built-in USB to JTAG converter module. On the software side, all this was done within Linux. I suggest using Linux as your operating system to do this sort of work. You'll need Xilinx Vivado 2014.4. We are going to eventually upgrade to 2015.1. Not too long from now, but for now, you can get away with 2014.4. For those of you that have E310s, the nice part is you can use the free Webpack version. For the X series, you will have to get a license for that because the FPGAs are larger in there, they require a license. Another thing is for simulation, you could find ModelSim to be very useful. It's a very powerful tool for HDL simulation, simulating what's going on inside the FPGA code. And then you'll need things like UHD, the user hardware driver, GNU radio, GRS, the sound tree module, and Martin he's provided a great instruction guide in the back there to pick up on how to get those various components installed. So let's just say that you went and you downloaded UHD, you followed the instructions, and you go to that directory and you see just a whole bunch of various folders, and you're trying to figure out, well, where's the FPGA code? Well, one of the first things you'll see is there's actually an FPGA directory. So you can go right in there, and that's where the FPGA code is. In that directory, you'll see 3 things. One, there'll be 3 folders called USERT1, USERT2, USERT3. USERT1 is the 1st generation USERT1 FPGA code. USERT2 is 2nd generation USERT2 in the N series. And USERT3 is our 3rd generation code in there. So all the FPGA code for our 3rd generation devices is in that USERT3 directory. If you go in there, the next level, there's a couple more folders, but the ones to really pay attention to is lib, which in lib there's another directory called RFNoC, and that's where all the RFNoC code lives, like the computation engines and all the infrastructure code. So that's an important one to know where that's at and to go take a look in there. And there's also a directory under USERP3 called top, and that's where your top level file exists for the FPGA code. And we actually have sub folders in there, one for each device. So for like the X300, you would go into there and you'd see an x300.b. Our code is written in Verilog, so that's the top level Verilog file. So if you're wanting to kind of start at the top with the X300 design, that's the file you go to and take a look at first. Now, in truth, when you're doing RFNoC work, you don't really need to look at that file at all. You're living in your sandbox, but it's interesting to know where that's at if you want to see the overall architecture. Building RFNoC images is quite easy. First of all, of course, you need to have Vado installed, 2014.4. And it's helpful if you install it in the default directory, which is underneath opt. If you just do what the defaults are in Xilinx, it'll do that for you automatically. The reason I say that is because when you want to go to your top level directory for your device, like USERP3 top X300 for the X300 or X310, and there's a script in there called setup in.sh. This is a script that you will run that will set up and make sure that you have the Vado installed and that its environment is set up properly before you go. And this is really nice because it's a simple script. You just run it and everything's ready to go. Or if you don't have something set up properly, it'll tell you and help you resolve that issue. And then our final step is that the RFNoC build infrastructure is makefile based. So in that top level directory, you just run make, and then you have a target, which in this case for the X300 would be the X310 HDS RFNoC. And that's it. You just run that, and eventually it'll spit out an image. It takes about an hour. If you use the Vado tools and you want to be able to see the GUI and work within the GUI, you can just type in GUI equals 1, and then the GUI will pop up. And it's quite easy. Having done a lot of FPGA development, it's pretty nice versus sometimes having to go through the GUI. It doesn't work very well. After it's ran for an hour, it'll spit out a bitstream file. That's what you program your FPGA with. That is in a directory called build. Also in there will be a file that's a report file that's useful for telling you utilization numbers along with, did your design make timing? This is always a problem with FPGA designs. Did it make timing? This will tell you whether or not you met your timing constraints. For the X300 series, what you'll do is you'll take that bit file, you'll use USERP X300 FPGA runner to program your X300. You can also JTAG download the image with the Vado. There's a capability as well. On the E series, we actually load the bit stream off of the file system that the ARM is running off of. UHD actually does this for you. So you can just copy that bit file over into the E300, to the specific place in E300 where the bit streams are stored, and it'll automatically load that particular file.
Is the E300, is that a Zinc chip?
Yes, it's Zinc based.
Okay.
Yeah. Yeah, so just to kind of go over that real fast, the Zinc is a dual-core ARM processor with FPGA fabric. So the E3, I call it E300, I mean the E310. If I ever say E300, I really mean E310. The E310 has that Zinc processor in it. It runs Linux, so it runs UHD natively from that Linux installation on there. It's kind of it's an embedded device, so it's kind of all integrated in one. So that means that the bit file lives within the file system on the E310, and UHD will take the bit file and program the FPGA every time you run it on UHD. And so therefore it's really easy to just replace that bit file with the RFNoC one. It'll pick it up and use it. Another interesting thing too about our makefile systems, we have two cleans, which I think is important to point out is we have a regular clean that just deletes that build directory for you. There's also a clean all. We break up our build system into a couple stages. One of the stages is building the IP separately, so that way the iteration cycle is faster. You're not rebuilding all the IP every time you try to build your design. That really makes it run a lot faster. Clean all removes those kind of directories. So if you want to go to a completely clean state because for something's broken, it's not working right, or maybe you added something, make clean all is the one you want to go with. But generally, make clean is the one that in most cases you did use. So that's getting started. We have a lot of information on the wiki as well that will complement this sort of information. So next, let's go ahead and jump into the anatomy of a computation engine. One of the first things about a computation engine that we need to know is the fact that they all have what we call a NoC ID. It's a 64-bit number that uniquely identifies that block type. So for instance, on our FFT core, it has a NoC ID. It ends up being like FF7, which FFT, Nice little correspondence there. And that's something that you will have to set as the user. That's not something that's automatically set up, so that's important to set up. The next thing on your computation engine is it has an interface to the crossbar, and it's highlighted up, or it's in red, and I have it highlighted. And at the bottom, if you look, I have a little bit of legend here that says that that's a cheddar interface. So what is cheddar? Well, cheddar is our packetization, or it's our packet format for RFNoC. So let's just do a quick little overview of what cheddar is. Cheddar stands for compressed header. There's a lot of history behind it. At one point we were using byte 49, but we weren't using, which is a protocol for SDRs that would allow SDRs to talk to each other with the same sort of protocol format. Eventually, we didn't use all the header information in this, so we called it like compressed byte. And then eventually we came up with this idea of cheddar, which is compressed header. So we have a very simple header here for our packetization format. It's that just the first part of the header is 64-bit. Well, all of our packets are, you can think of as being 64 bits wide. So each line of the packet is 64 bits. The first one has basically all the information you really need to know. For instance, it has the packet type. It has the ability to say whether or not you've included timestamp, EOB, and a burst, sequence number, length, in bytes, and a source SID standing for stream ID, and a destination SID, stream ID. All these in here also, if you've done networking, should look pretty familiar. The next line is this fractional time, 64 bits, so you can get a really fine granularity on the time base, and it's also large enough that your system could run for years and years and years and never have to roll over. And that's optional. You don't have to have it. The has time field is what determines whether or not that's included in the packet. Next is the payload, again, 64 bits. We tend to use, though, for our sample data, a format we call SC16, short complex integer. That means each sample is 32 bits wide with a 16-bit I, 16-bit Q, or 16-bit real and 16-bit imaginary part. So that means in the payload, each line, 2 samples fit. And another thing to bring up is the fact that we have these different packet types. We have data packet types, as well as flow control, command, and response. Those are really the 4 major ones. We also have this idea of for the data in a burst and for the response type, if it's a regular response or an error response type. Now, I brought up this idea of stream IDs, and I think we should go into really what is a stream ID, what does it mean? Well, the stream ID is what is identifying your endpoint in terms of, if you really look at the FPGA implementation, is how it really kind of hooks up to the crossbar. The way RFNoC is set up is it can be more generic than that, but the easiest approach is just to have it correspond with the crossbar. So in this case, it's 16 bits wide, so the upper 8 bits would correspond to what you could think of as the crossbar ID. So in your X300, you have a crossbar, you would set its ID, say to the number 2 or 7 or whatever. That would be that crossbar ID. In a different X300 device, it would have its own crossbar and its ID would be unique as well. And there would be some other number. And since it's 8 bits, that allows for 256 crossbars. And of course, you can think of them as crossbars or you can think of them as devices. Either way works. For the next 4 bits, we have the crossbar port. As I said, the crossbar is, in the first presentation, the most efficient implementation is 16 ports. The way our system is set up is more generic, where this could be bigger or smaller. You could adjust that. But in general, this is what we go with, is 16 crossbar ports, and so we have 4 bits dedicated to that. The next one is called the block port, and this is an interesting part of RFNoC. So each block internally could have 16, what you think of as destinations. And another way maybe to think about this is to think about like maybe key ports. You have your block where you're sending it to that actual block, but internally it has like these virtual sort of ports. But they're not really virtual in the FPGA because it really has to have dedicated bytes because all of them have flow control. So there's 16 internal paths, but they all share the same, if we go back to this picture, they all share that same highlighted bus up to the axis crossbar. So you can't just instantly talk to all 16 block ports at the same time. They do have to be serially written to.
Question from a random member of the audience. Can you give an example of what ports can use?
Sure, yeah. So there's really 2 big uses for them that we have an example computation engine where one of them is called add sub, where you basically take two different streams and you add them and subtract them, and the addition is returned on one block port and the subtraction is returned on a different block port. So that's a great way where you can use two different separate data streams from maybe two different sources and use them in your computation engine to do whatever you need for the calculation. That's one use. Another great use would be, say, the FFT core. Let's say you have multiple data sources that are coming in at a low data or at a low sample rate, and you're running your FFT core really fast at a high clock rate. Well, there's no reason why you have to have multiple FFT cores. Why don't you just have one with multiple block ports instantiated? And now all those various streams can just send their data to the FFT core, and it could round robin choose which stream it's going to process and try to be fair about it, and then return the results. And now you've time shared that FFT core, you've saved on FPGA resources. So those are two really good examples to use block ports. The next block in the computation engine is the NoC shell. This is part of the RFNoC infrastructure block that we provide that does a lot of work for us in terms of packetization and implementing flow control. So let's jump in here. One of the things I brought up in my first presentation is the fact that each RFNoC block is in its own clock domain. And so we have clock crossing FIFOs in there to allow you to go between those domains. That's a very typical FPGA design approach for doing that. Next is we have these cheddar packets that are coming in. And they have different packet types. So what we do is we have a sort of a mux demux approach here where the packets coming in from the crossbar, they're demuxed into different paths. A data path, a response, packet type path, command and flow control. And on the mux, on the bottom side going into the crossbar, same thing, is you mux those all together into one. Now generally what's happening is you have one packet coming in and then it's going, say, down the data path. You don't have them all just splitting off across all of them at the same time because that packet only has one type. One important thing to point out is on the data path, it has a FIFO in there. And I had said before that the way that RFNoC works is computation engines and blocks talk to each other over a FIFO to FIFO interface. Well, there's that FIFO in the path for you. Well, what's interesting to note here is it's only on the data path. And I'll address that in a second as to why it's on the other paths. So for this sort of FIFO to FIFO communication infrastructure, I also said that we had flow control. So we have two blocks in here that implement the flow control. The first one, the source flow control, the way that it works is it holds off data coming from the user and sending it to the next block downstream unless it knows that that block has room to accept that data packet. How does it know? Well, it receives flow control packets from that other block. And what sends those flow control packets from that other block is the bottom one there called flow control responder. And the way it works is it's observing that basically that FIFO to see when is it data getting read out. And as the data is read out and it realizes that there's room for an additional packet, it goes ahead and sends out a flow control response, letting the upstream block know, hey, you can send another packet. And finally, there's the command processor block, which you can see the command signal coming in from the top, comes in, and then there's something on the side called the settings bus, and then going out the bottom is this response. So the way it works is we have these command packets, or sometimes we also give them control packets. We use that term a lot of times interchangeably. The way it works is this is our interface to reading and writing registers. So we're trying to read and write registers in the computation engine, but we still need to have this packetized approach to go across our infrastructure. And so we have command packets that allow us to do that. But our register interface, it's not a packetized in nature, it's just a register that you read and write data to. It has its own address and data bus. That's what the settings bus is. In that command processor, it's converting that command packet into the settings bus, which is really simple. It's basically looking at the payload that has an address and data, takes that and just dumps it onto the settings bus. Also what happens is when you send commands, you also get a response packet that's like an acknowledge. But in that payload in there, there's also the value of a status register. Every time you send and write a control register, you get a response that's from what you think of as a readback register that you can select. And you might think to yourself, well, shoot, does that mean I have to write a control register every time I want to just read back status? You don't have to do that, actually. The way that the readback works is you select which register you want to look at through the command packet. So that's what you'd end up writing, is you would just say, I want to look at this readback register, and then the response packet would have this value. So that's RFNoC shell. That handles the packetization and flow control for us. But the output of it is still these data packet types. It's still cheddar, it's still a red arrow. It still has a header on it and everything. And what the user wants is, I promised before that we just get sample data. It's not packetized. And we need something to do that conversion for us. If you're very comfortable, though, with cheddar and RFNoC, you don't have to do that conversion. You could strip the header off yourself. But we provide something called AXI wrapper to automate that for you. So in AXI wrapper, we have data coming from RFNoC shell and to RFNoC shell on the left, and data going to the user IP on the right. On the left, the red arrows are indicating cheddar packets. On the right, I call them AXI stream, but you can think of them as just the sample data. Inside here, we have two blocks called the deframer and the framer, and their purpose is pretty simple. Rip off the header on the deframer, and then put a header on the framer. They're quite simple in that respect. We also added functionality, though, where you may not want to have to fill out all these fields of the header yourself. So what we do is we actually take the packets that we receive, and we keep a lot of that header information in a FIFO, because a lot of this information can be reused, like sequence number and the time. And for instance, packets that you receive, the source destination, or the destination could be used as the source. You can just flip those fields around when you send out your packets. So a lot of that information can be reused in a very generic fashion. So we have a FIFO in there for you to keep that. And the way that's activated this mode is through simple mode. Now, one thing that you'll need to provide, though, is the next destination. And that would be the next block. That's the destination state you'll need to provide. But it turns out that for most of our blocks that we've written and that you can write as well, the software side of things can control what that next destination is. So when you do radio, when you hook up the blocks, it'll automatically figure out what the next destination is supposed to be and fill it out for you. And you don't have to worry about it. And that's the approach I typically recommend people. Just use simple mode with AXI wrapper, and everything's handled for you. But there are cases where that may not be appropriate. One of the things that is assumed here is that your input packet size is the same as your output packet size, because the length will be the same. You reuse that data in the header. So if you're going to do things like that, you may need to provide your own header, and we have that capability. Finally, there's another path at the top here that's kind of interesting looking at control data, and we're going from the settings bus, which I said was for registers, reading and writing, and we're converting this to this AXI stream bus. What's going on there? Well, it turns out that a ton of IP out there, they really go with AXI stream, which is great. They use AXI stream for the sample data coming in, and they use AXI stream for the control data. And a lot of times that's a very simple, you just need to write an 8-bit value in there, but you also need to do the AXI control signals. That's what this path right here is doing for us, is we're still exposing it to the user as like a read-write register, but we're converting it to the right format for your IP to use. And I show only one path here, but these are parameterizable where you can have as many, almost as many control data paths that you want. So next is, I'll talk about the user registers. As I said before, we have the settings bus. That's a data address sort of bus. The address part of it's 8 bits. That means that we can have 256 registers. The size there is important because on FPGAs, I don't want to give you, say, 1 million registers. That would fill up the whole FPGA. And we found that 256 is a pretty good trade-off for size versus how many registers that you normally need. Now, the lower 128 are actually reserved for the RFNoC shell. We have various things that we set up, like flow control. And those are all reserved within the RFNoC shell. The upper 128, though, are available for the user. And every one of them is available, but there are a couple that I tend to use for interesting things. For instance, the next destination. If you're allowing UHD to control that with the AXI wrapper, that register of 128 is a good one to just have that set as the next destination. 129 and 130, that's that control data interface with AXI wrapper I was talking about, where you can write registers to those addresses and they get converted to AXI stream for you automatically. Finally, the user can have readback registers. And I said before that the way you do that is you write to the readback address, and then the return packet will give you the value at that particular readback address. 255 I tend to use for that. And in all of our example code, you'll see this where I did this over and over again. The final block to take a look at would be your user IP, which is very block specific, but there's some things I can talk about for it. One of the things is that we have a lot of basic building blocks already out there. And these basic building blocks are things like multipliers, adders, doing rounding, FIFOs, various utility blocks. They're all written with AXI stream interfaces, which means that you can drop them in and hook them up together really quickly. And you don't have to do a lot of additional writing of custom code. Now, there are going to be cases where you say you want to implement some very specialized algorithm. Of course, you definitely could have to write some custom code, but this is here to make it a lot easier. That's in the lib RFNoC directory. All this is in there. Some of the ones that are really important to point out on the utility side are these ones called like split stream, where you can take an AXI stream and split it into two. So say you're like cloning your stream, you want to have two paths for it, maybe for some sort of feedback loop. AXI join, that takes two streams and pulls them together. The reason I point these out is with AXI stream, they have this handshaking sort of protocol that goes on. That's not too hard. It's pretty easy to understand. But when you start splitting streams and combining them, there are some nuances that these blocks will take care of for you that it's just worthwhile using. Also, we have a library of existing RFNoC blocks, like the FFT, the window, FIR, vector averaging. I've shown those off. We have some nice utility blocks, like the keep one and in, a FIFO. Another thing is like packet resizer. The way it works on our packets is a lot of times we use the fixed packet size, but say you want a different packet size, that's a good block to go ahead and change that for you. One of the things that I'm working on is the OFDM receiver transmitter. Matt Edis is actually working on polyphase filter bank. So these are some things that are in development that will be coming up in the future at some point. Another really important one, especially for the E310 users, is this radio light block. So the way it is right now is our radio block includes DSP for like decimation, interpolation, filtering, all these things. On the E310 especially, that causes it to use up a lot of FPGA resources that the RFIC, the ADI 9361, could actually take care of for you. And so what we're doing is creating what we call this radio light block, where that DSP function has been ripped out, get all those FPGA resources back, and instead we'll have that as a separate DSP block that you can instantiate if you really wanted to, but especially on the E310, you don't need it. And that helps to get back a lot of FPGA resources. So for our next section, I'm going to go ahead and go through the FFT example. You'll find that in the RFNoC directory, not block FFT. It's based on the Xilinx FFT core. You can go from 32 up to 4K FFTs. The actual core itself supports up to 64K. I just didn't configure it that large because of the resource utilization, but you can go up that large. One of the guys I work with was asking me if I could do a 1,000,000 point FFT. I think there actually are generators out there for FPGA code that will do that large. I don't know if it'll fit. I don't know at all on that. Probably not. But that could be an interesting application, is having a 1,000,000 point FFT. It has a configurable output that's complex data or magnitude squared. Has this built-in FFT shift. And also what's really important, and I try to do this on all my blocks, and this is one of those tidbits I'll tell you about that'll be interesting to know, is you want to have no bubble states. And you may not have heard this term before. What's a bubble state? So in your computation engine, the FPGA, you have these AXI stream buses, and you're sending data across them. And they have this handshake. Well, what about if at some point in your code, you're sending sample data in, and it can't output a sample for every input sample you send in? Well, what would happen is it would have to throttle the upstream block. You'd have to say, hold on a second, let me do a little more computation. And what that looks like on the bus is a bubble state. It basically is, it looks like I'm not ready for a cycle or 2 cycles, or however long they have to wait. These bubble states are very easy to have in your design accidentally. You don't even sometimes realize it when you're hooking stuff up that you have this case where, for 1 clock cycle it needs to do something, get something ready. And what that does is that directly impacts your throughput. So say in my case I'm trying to run everything at 200 megahertz because I'm my ADB is running at 200 megasamples per second. So I'm running all my blocks at 200 megahertz. That means that for every sample I get, every clock cycle, I need to be outputting useful information. If I don't do that, then even if I have occasionally one clock cycle that I don't do useful work, or I don't output a sample, that would reduce my throughput to 199.99 megahertz or something. Well, at that point, we're going to back up because it has to be at least the rate or faster of my producing block. And bubble states is one of those that'll happen. I had to go through the FFT block pretty carefully and get rid of those. So that's something to keep in mind. So this is the FFT block. I filled out the various components in here. First one to point out, of course, is our RFNoC ID. That's the first thing that you'll want to make sure you get set up. Another thing is, a lot of your blocks out there won't really use command and response packets. They're not hooked up in the FFT, they're not hooked up in my FIR block, or my vector IR block, or a lot of them. Those are very useful if your block needs to inform other blocks to do something, or it needs to receive maybe a status register. Basically, if it needs to write or read control and status registers in other blocks, that's what that interface is really useful for. But the blocks that we have at this point, they don't need to do that. Of course, I have the AXI wrapper because I'm converting from that cheddar packetized protocol down to just the sample data AXI stream interface. We use the Xilinx FFT IP core. We have our FFT shift. The output, I have 3 outputs because they can be selected at runtime. We can select the complex data output, we can select the magnitude output or the magnitude squared, and those are all blocks that are written. Source code is there to look at, not really complex. So. And we have this little mux at the end that is controlled by a control register called magout that muxes between the 3. So in your software side, what you would do is if I wanted to select, say, the magnitude, I would write the appropriate mux value to select the magnitude output to register at address 133, which is magnitude output. Now, I was asked earlier about simulating your RFNoC blocks. What sort of support is there? And this is an important topic when you're doing any sort of FPGA design. What people quickly realize is that the iteration cycles are really long, and so if you make a mistake, even a dumb typo mistake, you can wait an hour before you realize that, oops, I misspelled the word reset, and now my whole system isn't being reset, and now I have to go wait another hour because I did a dumb typo. So people very quickly start doing simulations where it just makes the iteration cycle a lot faster. For RFNoC, I've written something called RFNoC Simlib to make that much easier. The idea is that you'll take your design under test, your computation engine, and you'll use RFNoC lib to automatically set up hooking it up to a AXI crossbar along with your test bench. And this is useful because what you're really wanting to do is do the test bench at a higher level where I'm sending in data packets and receiving data packets from my computation engine. And you could just, at that interface of right at the design under test, just inject it right there. But a lot of times you actually want to see what's going on across the crossbar. So you want to see, is it actually setting my destination properly? What does the traffic look like in a more realistic system? And that's what RFNoC Simlib is doing for you. It's setting up all those components to make it easy to test. And actually, this right here is right now standalone, but there's been a lot of great work on making this part of a more generic test system for our FPGAs. So RFNoC Simlib will change a little bit in terms of being a part of this more generic testing system, but it'll also be a lot even easier to use. But I will make sure you're aware of that. So in the FFT case, there's a test bench out there that basically what you do is you generate sine tones. They go into the FFT block, and then the FFT block responds with its results, and you look at the FFT bins and you say, okay, in this bin, is there a tone? Is it the right magnitude? And then the rest of the bins, are they all zeros? If there's anything different, then you know that there's something wrong with your implementation. And it could be as simple, usually the Xilinx core itself is written properly, so there's not a problem there. But sometimes it could be funny things like you unpack your data in a weird way, and so your samples are offset or something like that. All right, so you've built your computation engine, you hand-coded it, you've simulated it, it works great. Now how do you get it? How do I get it in my FPGA? It's quite simple. First of all, place your components in the RFNoC library. We're trying to make this into a more out-of-tree approach, where you don't have to still be within our directory structure to add it, but we're not there yet. So for right now, underneath usurp3 lib RFNoC, just add all your components in there. There's a make file in there called makefile.inc or include. It's very self-explanatory to add your files in there. You just add them. There's another file that's in the top level directory called RFNoC auto CEinst x3 or e310.b. This is the file that is hooking up your components to the crossbar and allowing you to instantiate your components. This would be the file that you need to hand edit, and it's also very simple and self-explanatory. But this would be the file that you edit to hook everything up to the crossbar. The interesting thing to note about there is it has the word auto in it, which maybe implies automated. It's not there yet, but that's what we're going to do eventually, where you don't have to edit this file. It's so easy right now that I haven't been super motivated to change that file, but eventually we're going to have it where it's completely automated. You don't have to worry about writing that variable code. You just hook it up maybe through like a graphical interface, and everything's hooked up for you. Finally, you just run make again, and then you'll have your bit file spit out for you. So for the final part of my discussion here, I'd like to talk about some of the FPGA design tips to hopefully help you guys out when you're doing some FPGA design, don't run into some issues. The first one I've already went over, avoid bubble cycles. I'm really a big proponent of this, but there could be cases where it's just too painful. If you do have bubble cycles and you just can't do anything about it, the flip side would be run the block at a higher clock rate. That works as well. Another thing is I talked about using our utility blocks like split stream. So when you're taking an AXI stream and you split it, use AXI split stream, especially split stream FIFO. The reason you want to do this is that when you're splitting these streams, imagine that they go down to some downstream block. And one's consuming data really fast, but the other one is consuming data extremely slowly. But what will happen is, as this one doesn't consume data, it'll back up to where the split occurred. And at that point, it'll say, hey, I'm not ready for additional data, so don't give me more data. Well, this other path, it consumed all of its data. Bam, there's a bubble. That's a bubble cycle path right there. Because this one is starving, it wants more data. The way to get around that is you could insert a FIFO onto the longer path, or the slower path, where you'd start filling up the FIFO, and then the other path that's consuming data more quickly could keep getting new data. Of course, one problem could be is that it really is a very slow path and it never runs any faster. The FIFO approach won't fix it, but in a lot of cases it turns out that's not true. Another thing is on the flip side, when you're combining streams, be careful about the paths having different latency. You'll have these designs where you'll have one path that splits and then comes back together, and those two paths will be of a different latency. They might consume data at the same rate, but this one takes 20 clock cycles and this one takes like 5. Well, again, you'll run into this bubble cycle case where the data will flow through this one really fast, but it'll take a long time to flow through here. Finally, when they catch up to each other, this side has been starving for a while, and this side has not. And if you insert FIFOs to balance the latencies there, you can prevent the bubble cycles from occurring, where everything just kind of flows through one clock cycle at a time. The one thing about that case, though, is generally in the simulator you need to figure this out. Unless you count the clock cycles, which sometimes can be difficult, usually in the simulator is how you figure out how deep the FIFO you need. Or you just throw in a decent sized one, and that works too. And the next set of tips, and this is actually my final slide before we go to Martin. The next set is be mindful of deadlock situations. I didn't go really deep into the details of how AXI stream works, but one of the rules in there is that you have this valid and ready signal. And the way it works is the upstream block asserts the valid signal when it has data available. And the downstream block, it'll assert its ready signal when it's ready to take that data. And when the valid signal's high and the ready signal's high, that means data is consumed. But there's a rule that says, if I say that my data is ready, if I say my data is valid, I cannot then say it's not valid unless I've gotten at least one clock cycle ready. Or in other words, I've consumed at least one clock cycle's worth of data. And the reason you do this is It's kind of like faking out the downstream block. It gets all set up and ready to take your data, then you say, I'm just kidding, I didn't have data for you. And that can cause actually a deadlock situation. And this is a rule that it's very easy to fall into, because when you're coding your thing up, you may decide, oh, I'll just say that I'm always ready when I'm valid, or I'll kind of tie those signals together, and sometimes it works, or sometimes you'll run into this case where the ready drops, and then you said, oh, I'm not valid anymore, and bam, you've hit a deadlock situation. So you got to be careful about that. One way to fix that is also, I say in the next block, which is be careful for ready valid combinatorial paths. That means saying that my ready and my valid are dependent on each other. Not only can it maybe cause this deadlock situation, you could also run into the case where I take a bunch of blocks and they end up having this really long combinatorial path that has horrible timing characteristics because you're going through 20 blocks. And that kills your timing results, and now you can only run at megahertz. The way to get around that in the previous bullet point is you could use AXI-FIFO, one of our utility blocks, and set it to size equals 0, which really what that does is that inserts what we call an AXI register. So it's like a 1 deep FIFO you can almost think of. But the nice part about that is it breaks up those combinatorial paths, and it automatically follows that rule of do not deassert T valid without T ready. The next one is also AXI stream, and it has to do with ignore the output when you don't have a T valid. This is actually more of a debugging issue. You'll be running your simulator and you'll see all this crazy data on the data bus, when it actually streams data part of the data bus. And you'll be wondering, what is all this? What's going on? It's going crazy. But you may not notice that it's not valid. And that's something that you need to keep in mind, that those other signals that are on that bus can do whatever they want as long as it's not valid. When they're valid, they better be right. When it's not valid, they might go and do crazy stuff. And that's fine, because there's optimizations you may do in the FPGA where you allow those signals to kind of just do funny things. And you could handle those cases to make them look nice, but that takes up more resources, so why not just let them do whatever they do? Just make sure you have the valid signal correct. And finally, I brought this up, I think I was talking about this before, is we have this crossbar statistics tool that's underneath firmware USERP 3 X300. This is, when I say firmware, that's in the UHD directory. X300 debug.py, it's a Python script. Really what it's doing is sending special packets to the X300 that allow you to read back the crossbar statistics. And that's really great because then you can know, how many packets have flowed from computation A to computation B. And it really helps you kind of drill down quickly. If one of your computation engines is just going crazy, you can know, oh, I sent it 1,000 packets, but it said it only received 900, or only replied to one of them. Gives you a good idea. So that is it for my overall presentation. I did have quite a few more slides, but in the interest of time, I went ahead and cut this down. When we post this presentation, you will see some more at the end that go over like the settings bus, AXI stream, flow control in more details. So it could be worthwhile to check out this presentation and look at the appendix section, and you'll get some more useful information. And so with that said, Martin will cover the software side for us.
Any questions for Jonathan while I set up?
Yeah, I hope is it happening? Oh, sure, go ahead.
So an AXI packet, this might have been covered earlier, I missed it, but the packet contains a block with multiple samples?
Yeah, so the cheddar packet structure is such that it has a header.
Yep.
And in the header, it has a link that tells you the length of the payload in, try to stand the camera over here. So it has a link that tells you the size of the payload in bytes. And so that's, the length is 16 bits, so you could have to the 16 number of bytes. Realistically, that's a lot. That's a big packet because you need to have a FIFO that can store that big of a packet on the receiving block. But yeah, the payload, it's 64 bits wide, so it can hold. Our samples are short, complex, 16 generally, although you can have different types, but that means that for 32 bits you have one sample, so the payload generally holds 2 samples per line. Does that answer your question? Anything else?
samples, staggered IQ.
Yeah. Yep.
So I thought ISE was going to be supported till 3.9. Is RFNoC a different situation? You need a Movado license, or is there anything stopping people from using ISE?
So right now, if you downloaded it at this very moment, it'll still be IC.
Okay.
I'm pushing the Movado stuff. That's why I made this presentation with Movado in mind. That's like changing the thing.
Okay.
So going forward with RFNoC, you'll be going with Movado. You can still stay with the older stuff, but you really do want to transition to Movado. It's a lot faster build times. The make file system is a lot cleaner and a lot more reliable. If you really want to stick with ISE, you could probably port some of the changes to ahead, or to backward actually. But you're eventually going to run into some problems.
Other question I had.
That's sort of true for non-RFNoC stuff as well.
Right,
You
yeah,
go from
I'm
master
aware.
into Movado because Xilinx recommends Movado for all 7 series tracks, so we're basically dropping support for ISE for all users.
And there's no new ISE versions coming out. It's 14.7. That's it.
So other question on the E310, how much on this radio light do you anticipate freeing up space?
So right now, we did some estimates, and we found that, so the E310 is about 70% full.
Right.
And we found of that 70%, about 50% of it is from that DSP functionality in the radio ports. So you could say about 35-ish% you'll get back. So that drops you down maybe as low as 30% to 40%. So you'll have around 60 to 70% free space after that.
Okay.
Thank you.
I'll be talking about the software development that you need to do as an RFNoC developer. And the question you might legitimately ask is, well, wait a minute, but I do have to do software development at all? Because, I want to do FPGA development. And I just want to remind you that this is something that we want to be able to use from a software stack. So it is controlled through UHD, but say we want to use radio, for example, and just interconnect those blocks, then clearly the software needs to be informed about what's going on in the FPGA. There is a lot of configuration that's going on, like setting registers and all of these things that can be dealt with very efficiently if we let the software stack do that for us. And here's an example of how this looks like. So I don't know if we've actually mentioned this, but you can see like the arrows have different colors. And you can see like the green colors, these are RFNoC connections, and then the dashed ones are when we cross over domains. And this is a flow graph where part of the blocks are actually scheduled and handled by GNU itself, and the rest are handled by RFNoC. Now, but what we really want is, we do not want to care about this. We just want to take away these boundaries. It should all be transparent. And to make these domain crossings very, very simple, we need to set up some software configuration, because GNU does not take care of these blocks at the moment. So what is the actual job of the host side of UHD and GNU? Well, configure the connections. Obviously, it's like inform the blocks that they are now streaming from one to the other. Setting all these registers in an easier way than like I don't want to say, okay, let's poke this hex number to this register address. I want to say, okay, change the FFT size to 256, and then someone else should take care of what actually that entails. Also, whenever we have these domain boundary crossings from radio handled blocks to RFNoC handled blocks, we need to set up a stream, and that depends on how the user is actually connected. Is it PCIe? Is it Ethernet? Is it AXI? And we don't want to care about that either. So there's a couple of things that we really, really don't want to handle while we're actually doing the application development, and that's why we need to do both sides. Well, so this is the part of the flow graph that is the previous flow graph that is RFNoC. When we're using GNU Radio, we have additional features that we want to take care of. So, for example, in GNU Radio, if you connect blocks that don't match type, you'll actually get an error. It might be computationally possible to stream data from, I don't know, like encryption block into an FFT block, but in most cases you don't actually want that. So we're using data type checking. And once we're in the RFNoC domain, RFNoC needs to take care of that. So this is a more detailed example of what happens. So in this example, we're streaming from an FFT block to the vector IIR. And we say, okay, connect these blocks. And there's actually a command that's called connect. And what happens when we do that? So first of all, we figure out who these blocks are, like what their actual numeric address is. And then we figure out that the FFT block streams complex samples in a vector format, and luckily the vector IIR handles complex samples in the vector format. We've even set vector size. You can see FFT size on the left and vector length on the. Oh, thank you very much. Huh. Thanks, fantastic. You can see like that these vector sizes match. So if they wouldn't match, then someone needs to throw an error. And that is so we do all these checks, and then once they all pass, then we actually start calling, or like we start peeking and poking. So the upstream block needs to be told that which address to stream its data to. That is a poke. So all the peaks and pokes are highlighted in green. We figure out that the packet sizes are fine. That's similar to checking that the vector sizes are the same. And then finally, we have to set up flow control. Jonathan talked about that. And it's actually like a multiple peak and poke process, because this block needs to know how large its input size FIFO is, etc., etc. There's so many things that, first of all, we don't want to care about them. But even if we did, like, these are always the same. Like, do we really want to do all of these? No, we just want to call connect and have the software handle those. Okay, so a full stack or to do radio integrated RFNoC blocks entails much more than just the FPGA side. It's also something on the UHD side, and then possibly something on the radio side. Now, this looks pretty complicated. Like, we already had to do all this work. You know, we need to add 4 more files. Well, actually, it's not. This is actually the worst case. And if you're lucky, then you can actually just use these descriptor files, and you can use default code for this part. It might get even easier if you're not using the radio, but just like raw UHD and attaching that to your own application. Then you might actually get away with a single XML file that describes the contents of your RFNoC. So let's walk through the steps. So the assumption is that you follow Jonathan's talk and you synthesize your IP. And I'm actually going to try and stick with the FFT example that Jonathan used for most of my presentation. Let's say that all works, it's tested, it's guaranteed bug-free. So now we want to put that into UHD. The first thing that we do is we write a block declaration file. Now this is an XML file. And it contains the NOC ID, and then it describes the block. So what kind of arguments can be set, how are the input and output ports defined, and what are our registers. And instead of just talking about this, I might just show you one of these files. So this is the actual file that runs the block. So going from top to bottom, first of all, we define the NOC ID, and they are 64-bit, but we have this shortcut thing where you can just specify the first couple of bits, I guess the first 16 bits. Then we name all the registers, and we give them we give them actual names. So the FFT reset register is the one that's called 131. And after we've done this, we never ever need to go back to this numerical value. We don't care. We define it once, we call it FFT reset. There's a couple of other registers. This is the FFT size, and we also have readback registers where we can query information from the block, and we might be using them as well. So the arguments are actually something that are specific to the host cell. So we have an argument that is called SPP, and that is samples per packet, but it is also identical to the FFT size. Why did I call it SPP? Well, most blocks call it SPP. On the FFT block, we could have called it FFT size. It might have been more descriptive, but this is more consistent with what we use. And these are all our arguments. So SPP is of type integer, and we give it a default value. And now this is interesting. We pass in this code that gets called and interpreted at runtime. And this code is a DSL specific to NoC descriptions, and it's, we call it NoC script. So whenever you try and change this value from software, it'll actually run this code to check. You can see there's like two AND concatenations. So we have like the value must be greater or equal to 16, lesser or equal to 4096, and it has to be a power of 2. And if that check passes, then we actually go on to this next line of NoC script where we set the values, the actual registers. And you can see we're using the numeric names. So this is the access config register that Jonathan mentioned earlier. It's a default register. We didn't have to declare it up top. But here, for example, we are setting a specific register by name to the log2 of this value of SVP, which we know is actually a power of 2 because we checked this before. Okay? So if you have simple checks and actions like these, you do not have to write C++ code. This is all you need to do. In this case, so this, if you've never heard of this before, not a surprise, we actually just finished it last week, so this is pretty new. So for the FFT block, we don't really need the C++ code anymore, but we still have it around because I've added that, but I haven't removed the actual file. Just to finish the XML file first, we also define the ports. And if you've ever written GNU Radio code before, where we have similar files, you'll notice that the port declarations look very similar. And that was done deliberately because we assume that there's some overlap between RFNoC developers and GNU Radio developers. So you do not have to relearn. One thing that's interesting is that you can use the arguments that we declared above inside this the port declaration. So here we have sync as an input port. We give it a name in, very simple. We define its data type statically to SC16, so we can only put in complex sample data. And the vector length is always the FFT size. Now if we try to, let's say we put an IFFT in front of that with a different vector length, UHD will figure this out by itself. Okay, so, oops, not intentional. The block declaration, the simple XML file. So NoC script, as I mentioned, very new. It's a statically typed interpreted language. It gets evaluated as late as possible at runtime. It looks a bit lispy for those who care about that. But the most interesting thing is that anything that is expressible as a very basic expression can be expressed in NoC script and thus saves you from writing any C++ code. Now, in many other cases, you do need C++ code, and that is the block controller class. Now, something I just glossed over but kind of alluded to was the fact that every RFNoC block that is actually FPGA fabric on the FPGA is represented by a C++ class that is instantiated and running inside UHD. And this is sort of how we keep track of the states of the connections. So these C++ classes, they are connected in a logical fashion in the same way that the FPGA blocks are connected. So we connect the FFT to the vector IIR. That means on the host side, the C++ class that represents the FFT block is connected to the C++ class that connects the vector IIR. Only we do not transfer data between these. That happens on the FPGA side. So these block control classes can be written specifically to your blocks. In this case, you write them in C++. There is a large number of API calls that you can use to access the FPGA inside those blocks. And I will show you the FFT implementation in a second. But first of all, the question to ask is, when do I have to write this? And basically the answer is whenever you can't express the functionality that you need within your XML file, including NoC script. So something that is very complex, you won't be able to express it in NoC script. And we could make NoC script more and more complex to facilitate that, but that's kind of beating the purpose. At that point, you just might as well write the control class in C++. And for example, the radio controls, they do a lot. They do lots of things. They have to control many registers. There's many specifics that we need to take care of, so we're not going to bother trying to express them in pure NOC script. So if you do that, the problem you're facing is that you need to sort of integrate those files into your build system, which you do not have to do if you go down the pure XML file route, but it does give you more control. So the idea here is make it as complex as necessary, but give you all the features that you need. So if you need the high complexity, you will have to put in a bit more work. So the corresponding file looks like this. So this is a header file that declares the interface, and you'll see functions like set magnitude out. This defines the type of output. So is it complex? Is it a magnitude squared, etc., etc.? And then the corresponding C++ file looks like this. We have functions like these, set magnitude out, and you can see there's a function called srWrite, settings register, and this looks pretty, like this is pretty easy to understand. Magnitude out is the name of the register. We define that in the XML file, and then we just pass in the value that we actually want to set. And in a similar fashion, if we want to set the FFT size, I still have this function here for presentation purposes. We call this line, and it will do the same thing. So the actual poke to the register is abstracted in a very readable fashion. Any questions on that part?
There's one line just above that. What was the line above that with the AX, right?
Oh, this one?
Yeah.
Yeah, well, it's basically the same thing. In this case, we don't use a named write. So this is, I'm mixing two styles here of poking. This is more C++-y, and also this value is a magic constant that we currently use. This is something that will be allowing users to set sometime in the future, but at this point it's just a magic number that makes the scaling look nice. Any other questions? Okay, so at this point, this is all you need to integrate RFNoC into UHD. So you've written your FPGA IP, you've written your XML file that describes that, and that's it. So I'm just very briefly want to explain what actually happens on the UHD side when we fire up the user, the device driver. So because when we fire up when we just boot it up, we don't know what computational blocks are there. So what we actually do is we have a dedicated register which is always the same, that just returns the NOC ID. So we actually look this up. So we go like port by port, so we port number 0, we ask for the NOC ID, and we get back this hex value. And then we go through our XML files. We find an XML file that matches this value, and in this case we found one. And we now know it's an FFT block because the name is also encoded in here. We know all kinds of other things as well, such as the ports. From the name, we actually can look up in a registry if we have a dedicated C++ class that will control this. If not, we will use a default C++ class, which has most of the features implemented. Yes, that's pretty much it. At this point, before I go to the GNU Radio side, I just want to point out that our UHD manual that we have on our website is actually matching our current releases. But we do update the manual on our feature development branches. So if you're writing RFNoC, for example, you build your own manual, you can see it gets its own RFNoC version in there. This is not the same thing that you'll find on the website, but it includes all these static information snippets that you will need to write code. For example, the CWIDER or cheddar protocol is included in the manual. And more importantly, all the classes that you need to write your own blocks are also here. So a base class that your block controllers will inherit from is, where is it? It's called block controller base. There it is. You can see there's a bit of a wild inheritance structure, but this looks a bit worse than it actually is because the software I use to create these graphs doesn't resolve diamond inheritance. But you can see these are functions that you can use inside your code. And they are pretty self-explanatory, but even if they're not, you can click them, and you'll get a description. So srWrite is a settings register write function, and you can just use these functions as you wish. And you can access the information you put into your XML file. Okay, so now assuming that you want to integrate this into the radio, there's some more effort that you need to do. Just one thing I want to clear out before this gets confusing. We have GRUHD, which is a part of the radio, and we have GREdits. Now the idea is, as things mature, we move them from GREdits to GRUHD, that this is our staging ground where we just can go wild. Whereas this is why we want to provide a very stable API. And this has been in radio for a long time. So GREdits is an out-of-tree module that you can download from GitHub. I think it might be on the handout. If it's not, the URL is here. And it's also mentioned in the wiki page that Jonathan pointed out. And currently, all the codes that you need to run the examples are in GREdits. Now, the first thing that you always need to do in radio is you write a block that controls, does your signal processing. And for RFNoC, this isn't any different. However, we provide a block called RFNoC generic, which is a fully featured block. It does everything. And if you just parameterize it right, in most cases, you will be able to use that. So the FFT block actually uses this. There is no C++ code in radio to control the FFT block. But there is a block that the window function actually has a radio block. And you might wonder why. And I'm going to show you why. It's actually quite simple. So this is, if you've ever written radio code, this will look very familiar. This is a block declaration. It has one function called setWindow here. Otherwise, it has a constructor which the details aren't that important, except for the fact that you can already pass in the window tabs in the construction phase. Now, I did not open that file. That would be a shame. Not a problem. I know exactly where it is. So the problem that we face here is in RFNoC, you can actually change the window size at runtime. In radio, you can't do that because stream signatures can't be changed without stopping the flow graph. And this is the one case where the GNU radio behavior is a bit different from the RFNoC behavior. So we actually just have this. The whole reason we need C++ code here is the fact that we need to run this little check in here before we can actually call the appropriate function. But you can see doing that is pretty easy. We just get a pointer to the actual block control class here, and then we call a function called setWindows. So writing blocks, the C++ blocks with the radio is pretty simple, and gmodule still applies. You just need to change some minor things. One thing I didn't go into details, but you should keep in mind if you have to write your own blocks, is that they will derive from RFNoC block instead of GR block. And if you don't know what that means, it doesn't matter. You probably don't need to. So, but finally, to be able to use it in GRC, you need to write another XML file, the GRC bindings file, which is, I already mentioned another XML file. What is important to point out is if you didn't write a C++ file, you still need to write that. But it doesn't prohibit you from customizing the GRC bindings. So the FFT block, for example, I said it doesn't require any C++ code, but what we do have is our custom XML file. So just to very briefly show you how that looks like. You can see we instantiate a RFNoC generic class. We pass in some things that we need to specify. And what's interesting is that this RFNoC generic takes in all these arguments that are very, as the name says, generic, but we're actually specializing them in here. So the rest of this looks like a typical GNU Radio XML file, which I unfortunately don't have the time to explain in detail. And the parameters are exactly what you'd expect, the FFT size and the output type, so the ingredients I actually put in this drop-down menu where all the valid values can just simply be selected. Then we have the output type, magnitude out, complex, etc., etc., etc. And finally, the port definitions. And as I mentioned before, these look very similar to what we have in the RFNoC XML file, because the RFNoC XML structure was actually modeled after this. So what we might actually provide in the future is a tool where you just take the RFNoC XML file and then create a skeleton file that will work with GRC that you just need to fill out to suit your needs. Okay, that's pretty much all there is, unless there are any more questions. None? Okay, very, very good. Just to wrap this up, on the host side, we do require some modifications, but they are pretty simple. Best case is you write 1 or 2 XML files. I mean, there's lots of examples for those. So if you want to see how we did this, look at the GREdit out of tree module. Same goes for the case where you need to add C++ files. We did try and make the host side development as simple as possible, and I think we got it down to probably the simplest that we could get it. I doubt that we can make it even easier at this point. Maybe you can add some graphical tools to help developing this, and other tools such as Geomodel that are already out there are still usable. Okay, in that case, thank you very much for the question.
We talked a lot about timing and what we do with flow control. What do you do with the UHD and also the new radio if you can't keep up? You have to support all kinds of processors running.
Not really. GNU Radio has always been agnostic of the actual, underlying speeds. So
it just throws data out.
Sorry?
You'll just throw data out.
No, you don't. You just back up and you just wait what happens. Now, if you have multiple clocks in there, and that happens a lot if you do sound card processing user, then you will get run into issues. And one of the 2 pieces of hardware has to make concessions, and they will throw data out or produce underruns, something like that. But that's something that you usually want to avoid. You usually want to set up your processing chain that doesn't happen. But if you look at the examples that Jonathan showed earlier, where it's just host side producing a test signal, and then on the host side we inspect the output in a graphical widget, for example, it doesn't matter. GNU Radio will just adapt. It will just produce data as fast as RFNoC will be able to process it. And that's it.
In that example, I noticed there was a throttle block, which I thought you don't really use with the hardware hooked up. Was there a specific
Okay, that's a
reason
good question. It comes up all the time. So that's actually not the entire truth. You don't need a throttle block when you have a hardware clock. The RFNoC blocks themselves, okay, they have the bus clock, and maybe we could leave it out, but you also want to make sure, actually what happens if you leave out the throttle block?
So what happens is, in RFNoC, you don't have a sample clock when you're generating samples from within your radio. So RFNoC's just running as fast as it can get data in, which will likely your limitation will be the gigabit Ethernet interface. So if you leave the throttle block out, it's probably, if you were to look at your throughput, it's probably the throughput of your gigabit Ethernet interface. That's just as fast as data can come in. And since you don't have a sample clock, really the data is just at whatever kind of sample rate you want to think in your mind it is. Now, by adding the throttle, you're kind of fixing, in a way, a sample rate. But even the throttle, since it's software-based, of course, won't be perfect. It'll probably be pretty close. But at least then you actually are throttling, where if you look across gigabit Ethernet, it looks like about, say, a megasample per second with the data that's going across there.
Yeah, so if you left out the throttle block, it would work, but you'd have similar issues to when you run a pure radio photograph without the throttles. Also, so because we do visualization, it makes the examples work much